When people hear the words space and time, they usually imagine two entirely separate ideas. Space feels like the empty stage where objects rest and move. Time feels like an invisible clock ticking steadily in the air background while events unfold. This picture works perfectly well for navigating daily life, and it feels utterly natural because every moment of lived experience trains us to think exactly this way. Physics itself began with this same comfortable picture. Early scientists treated space as a fixed, three-dimensional grid, stretching infinitely in all directions, and time as a universal rhythm beating at the same pace everywhere across the cosmos. Events happened somewhere in space, and they occurred at some particular moment in time. The two concepts stayed politely separate, like coordinates written in different columns of a ledger. Then something remarkable happened. Careful measurements began to whisper that something much deeper was hiding beneath this simple picture. Light turned out to behave in an extraordinarily peculiar way that defied common sense. No matter how fast an observer traveled, no matter in which direction they moved, light always traveled at exactly the same speed, walking directly toward an approaching beam, chasing it in the fastest rocket, standing perfectly still on Earth's surface. Every single measurement agreed with stubborn consistency. That one singular fact forced a quiet revolution throughout physics, because speed fundamentally connects distance and duration. If the speed of light must always stay fixed, then distance and duration can no longer remain independent of each other. Space and time began to lean into each other, blending together in ways that transformed our understanding of reality itself. What emerged was something both simpler and stranger than anyone had imagined, a unified structure that would reshape physics entirely. Imagine describing any event in the universe. A distant star flashes suddenly, a bell rings in a tower, a subatomic particle spontaneously decays. To locate that event precisely, one must provide both a position in space and a moment in time. Physics gradually discovered that these two pieces of information blend together in an unexpectedly precise and elegant way. Change the motion of the observer measuring that event, and the split between spatial distance and temporal duration changes accordingly, yet the combined description remains perfectly consistent across all observers. That combined description receives a single unified name: spacetime. Spacetime treats every event as a single point with four numbers attached to it. Three numbers describe where in three-dimensional space the event occurs. One number describes when, in time, it happens. The genuinely surprising part lies in how these four numbers relate to one another in the mathematical structure of reality. Different observers moving at different speeds may genuinely disagree about measured distances and measured durations. Yet, they will always agree about the space-time separation between events, something deeper and more fundamental than space alone or time alone holds the entire fabric of reality together. This unified perspective explains effects that once sounded like impossible paradoxes. Moving clocks genuinely tick at different rates than stationary ones. Lengths measured along the direction of motion genuinely contract. None of this comes from faulty instruments, peculiar materials, or measurement errors. It comes from space-time itself, which naturally assigns different slices of distance and duration to different observers based on their motion. What one observer calls purely spatial distance, another observer moving differently might partially experience as temporal duration, and vice versa. A remarkably useful way to picture this involves paths through space-time. Every object that exists traces a continuous path through space-time, called a world line. An object standing completely still in space still moves relentlessly forward through time, so its world line points purely in the temporal direction. An object moving rapidly through space traces a world line that tilts, trading some of its motion through time for motion through space. All objects continuously move through space-time. They simply choose different directions within that four-dimensional structure. This single geometric idea replaces many separate and disconnected rules that once seemed fundamental. Instead of asking separately how space behaves and how time behaves, physics now asks the unified question of how space-time behaves, motion, light propagation, cause and effect, simultaneity, all follow naturally from that underlying geometry. Once this viewpoint settles into understanding, the universe begins to look less like a static stage with independent actors performing on it, and more like an intricately woven fabric where events, motion, and measurement all share the exact same fundamental structure. The fabric maintains its own internal order, quietly guiding everything that happens within it according to consistent geometric rules. Once that revolutionary idea truly settles in, another profound shift follows almost automatically. Motion stops being something measured against a fixed, absolute background. Instead, motion becomes a comparison between different paths taken through spacetime. Two observers moving at different velocities are not arguing about whose measurement reflects true reality. They are simply slicing the same unified spacetime in different but equally valid ways. This is precisely where time stops being universal. There exists no single master clock ticking at the same rate for the entire universe. Each object carries its own personal measure of time along its unique path through spacetime. A wristwatch strapped to your wrist measures how much spacetime that particular path passes through as you move. That measured amount is called proper time, and it belongs intrinsically to the object itself, to that specific world line. Two observers can separate from each other, move through spacetime along different paths, eventually reunite at a later event, and honestly report genuinely different elapsed times on their clocks without any contradiction whatsoever. Space-time allows this, encourages it, demands it. This sounds impossibly strange only because everyday speeds completely hide the effect. At typical human scales and velocities, the differences remain absolutely tiny, far too small to notice without extraordinarily precise instruments. At higher speeds approaching the speed of light, the differences grow dramatically at exactly the speed of light itself. Something truly remarkable happens. Time measured along that path stops entirely. For a photon of light, there exists no passage of time whatsoever between the moment of emission and the moment of absorption. That fact is not poetic license or metaphorical language. It falls directly out of space-time geometry as a mathematical necessity. Light traces the boundary structure of space-time itself. It marks the absolute limit of cause and effect, the fastest possible connection between events lying outside that light. Speed boundaries simply cannot influence each other causally, not because of technological limitations we might someday overcome, but because space-time itself does not connect them in the geometrically required way. Cause and effect are not arbitrary rules imposed afterward by philosophers. They are built directly into the geometric structure of space-time from the foundation up. This fundamental structure also explains why simultaneity loses its absolute universal meaning. Two events that appear perfectly simultaneous to one observer moving at one velocity may not appear simultaneous at all to another observer moving at a different velocity. There exists no single objective answer to the question of what is happening right now everywhere throughout the universe. Each observer carries a personal slice through spacetime that they naturally call the present moment. Right now, everywhere throughout the universe, each observer carries a personal slice through spacetime that they naturally call the present moment. The universe itself does not privilege any one observer's slice over another's. All are equally valid descriptions of reality. Once this perspective is genuinely accepted and internalized, space-time stops feeling like an abstract mathematical construction divorced from reality and starts feeling intensely practical. Satellites orbiting high above Earth experience time measurably differently from atomic clocks sitting on the ground. Their paths through space-time differ based on both their velocity and their position in Earth's gravitational field, so their clocks tick at observably different rates. Global navigation systems must carefully correct for these relativistic effects, or they would accumulate errors of several kilometers per day, rendering them completely useless. The theory does not live only in physics textbooks and academic papers. It runs constantly and quietly inside the technology we depend on every single day. The implications ripple outward to all of physics. Energy and mass turn out to be related through the structure of spacetime. The famous equation relating them is not an isolated fact, but a direct consequence of how spacetime treats motion. An object at rest possesses rest energy. An object in motion possesses additional kinetic energy. Both are expressions of how that object moves through spacetime. Mass itself represents concentrated energy moving primarily through the time dimension rather than the spatial dimensions. This unified picture transforms what once seemed like disconnected phenomena into aspects of a single, coherent structure. Length contraction, time dilation, the equivalence of mass and energy, the behavior of light, the structure of causality, all emerge from the geometry of spacetime. Learning to think in terms of spacetime is not about memorizing lists of strange relativistic effects. It is about adopting a fundamentally new way to organize physical experience. Instead of asking where something is located and when it happens as two completely separate questions, spacetime asks how events relate to one another within a unified four-dimensional structure. Which events can possibly influence which other events? How much proper time accumulates along any given path? How the geometry itself shapes what remains possible. Then gravity enters the story, and spacetime deepens yet again into something even more remarkable. Instead of treating gravity as a force pulling objects together across empty space, spacetime describes it as curvature, a bending of the geometric structure itself. Massive objects alter the geometry of spacetime around them. Paths through spacetime that once appeared perfectly straight to begin to curve, not because something actively pushes or pulls them off course, but because the very meaning of straight has changed in the presence of mass and energy. An object moving freely through curved spacetime with no forces acting upon it except gravity simply follows the straightest possible path available through that curved geometry. That path is called a geodesic, the four-dimensional equivalent of a straight line in flat spacetime, falling, orbiting, drifting through interplanetary space. These are all expressions of pure geometry, not the result of mysterious forces. Remove all other influences besides gravity, and an object simply follows spacetime's natural shape like water flowing downhill. This elegant picture explains why all objects fall at exactly the same rate in a gravitational field. Regardless of their mass or composition, they are not being pulled with different forces that happen to balance out. They are all following the exact same underlying geometry. A feather and a hammer dropped on the airless moon fall together. Because they both follow identical geodesic paths through curved spacetime, The motion comes from spacetime itself, not from any force acting through space. Time itself feels this curvature profoundly. Clocks positioned closer to massive objects tick measurably more slowly than identical clocks positioned farther away in weaker gravitational fields. Once again, this is not mechanical stress, electromagnetic interference, or measurement artifact. It is pure geometry, assigning genuinely different amounts of proper time to different paths through curved spacetime. Space and time no longer act as separate, independent players in the cosmic drama. They respond together as aspects of a unified whole. Mass and energy tell spacetime how to curve. Curved spacetime tells matter and energy how to move. This mutual reciprocal relationship replaces the older Newtonian idea of forces acting instantaneously across empty space. The replacement is not just mathematically elegant, it makes testable predictions that differ from the older theory, and thus match observations with extraordinary precision. At this point in understanding, space-time begins to sound less like a passive background stage and more like an active participant in physical processes. It expands, contracts, bends, stretches, ripples, and evolves dynamically over time. The universe does not simply sit inside space-time like actors on a stage. The universe fundamentally includes space-time as an essential part of its physical content, inseparable from matter and energy. The cosmic expansion fits naturally and elegantly into this dynamic view. Distant galaxies move apart from each other, not because they physically fly through static space at enormous velocities, but because space-time itself grows and stretches between them. No central point or edge exists where the expansion originates. Every location throughout the universe sees the exact same expansion pattern because the geometry itself changes uniformly. An observer in any galaxy sees all other galaxies moving away and measures the same expansion rate. This is not an optical illusion or coordinate trick, it is the literal expansion of space-time. Even complete emptiness is no longer truly empty in this picture. Space-time itself can ripple and vibrate, carrying energy and information across vast distances. Gravitational waves are traveling distortions in the fabric of space-time itself. When two massive objects like black holes spiral together and merge violently, they shake space-time so powerfully that ripples spread outward at the speed of light. Detectors on Earth measure these ripples as extraordinarily tiny changes in distance, far smaller than atomic nuclei, yet perfectly real and measurable. Space-time itself vibrates like a drum when struck hard enough. At this stage of understanding, space and time stop being mere containers for events and start being relationships between events. Distances, durations, motion, causality all emerge from properties of this single unified structure. Learning space-time deeply is not primarily about memorizing catalogs of effects or solving specific problems. It is about adopting an entirely new way to organize and is to understand experience itself. Instead of asking where something is located and when it happens as separate, disconnected questions, space-time asks how events relate to one another geometrically. Space-time asks how events relate to one another geometrically. Which events can possibly influence which other events given the structure's causal limitations, how much change and proper time fits along any given world-line path, how geometry shapes and constrains what remains possible. Once reality is seen through this lens, many puzzles and apparent paradoxes lose their mystery completely. Slowed clocks, curved planetary orbits, cosmic expansion, fundamental limits on signal speed. all follow from one internally consistent geometric picture. Nothing special or ad hoc needs to be added. Nothing hidden or mysterious needs to be assumed. Space-time does not explain absolutely everything about the universe, but it explains why so remarkably many things fit together so tightly and precisely. It provides a unified language where motion, gravity, light, and time all speak the same fundamental grammar naturally. Understanding that geometric grammar makes the universe feel less bizarre and strange, not because it becomes comfortingly familiar in the everyday sense, but because it becomes deeply coherent. The fabric requires no intention, awareness, or purpose. Its mathematical structure alone guides the unfolding of events, patiently and precisely, everywhere and always, according to consistent rules. Once spacetime is understood as a dynamic structure rather than a static stage, another quiet but profound consequence appears. Events themselves become more fundamentally important than objects. Physics stops asking what something is in complete isolation and starts asking how. Events connect to one another through spacetime. A collision between particles, a flash of electromagnetic radiation, a biological heartbeat, a conscious thought, each is fundamentally an event located in spacetime. And spacetime organizes precisely how these events can relate and influence each other. This is why spacetime cares so deeply about fundamental limits. A maximum speed exists not because motion becomes difficult or requires infinite energy, but because spacetime geometry allows only certain types of connections between events. Light sits precisely at that boundary. Anything moving slower than light can potentially be influenced by many events. In its past light cone, anything attempting to move faster than light would require somehow skipping over space-time structure itself, which the geometry simply forbids. The speed limit is structural and absolute, not technological or practical. This boundary shapes reality in profoundly practical ways. It decides what can possibly be known, what can potentially be affected, and what can never be causally connected under any circumstances. Two events can be extremely close together in spatial distance, yet remain completely unreachable across time. Other events can be enormously distant in space, yet remain causally linked through light speed signals. Spacetime does not measure meaningful closeness by meters or seconds alone. It measures separation by whether causal influence can possibly pass between events. This geometric structure is where trained intuition from everyday life begins to soften and transform. Distance is no longer just how far apart. Time is no longer just how long between. Separation becomes a question of space-time intervals, a combination of spatial and temporal separation that determines causal structure. Some separations allow influence and interaction. Others forbid connection forever, regardless of technology or energy available. This geometric idea alone explains why the past feels absolutely fixed, while the future feels genuinely open to possibility. Events in the past sit inside the region of spacetime that can causally influence the present moment. Events in the future do not yet have that relationship. That profound difference between past and future is not psychological projection or human bias. It is built into the geometric structure of cause-time itself. Space-time also explains clearly why changing the past remains impossible. It is not guarded by logical paradoxes or mysterious protective mechanisms. The geometry simply does not permit world-line paths that are loop backward through time in the required way under ordinary conditions. The structure blocks them as geometric impossibilities. Time travel to the past is not forbidden by law or causality, it is forbidden by geometry. At this point, space-time might start to sound rigid, deterministic, almost unforgiving in its geometric strictness. Yet paradoxically, it also allows extraordinary freedom and flexibility. Different observers moving at different velocities carve space-time into space and time in radically different ways, and all of their measurements are equally valid descriptions of reality. No observer owns the objectively correct present moment. Each carries a personal reference frame shaped by their motion and gravitational environments. This dissolves completely the idea of a universal now existing simultaneously everywhere, replacing it with many consistent but different viewpoints, all layered on the same underlying structure. That realization feels deeply unsettling at first, challenging fundamental intuitions about shared reality, but it actually simplifies physical description dramatically. Arguments about which observer measures the true values fade away as meaningless. The geometric relationships do not change between reference frames. Only the coordinate labels do. Space-time itself does not care how humans choose to label and slice it. The structure remains invariant. Then something even deeper emerges from careful analysis. Energy and momentum are not separate bookkeeping tools, floating abstractly on top of space-time. They are tightly linked to its fundamental structure through deep mathematical connections. Motion through space and motion through time are two complementary aspects of the same underlying phenomenon. Change one component and the other responds automatically to maintain consistency. This is precisely why energy, mass, and momentum transform together in specific mathematical ways. When observers change their reference frames, mass turns out to be highly concentrated energy moving primarily through the time dimension of space-time. Light, at the opposite extreme, is pure energy moving entirely through spatial dimensions with no motion through time whatsoever. Everything else in the universe lies somewhere between these extremes. This is not poetic metaphor or loose analogy. It describes exactly how space-time measures and relates motion. This deep connection also explains why adding energy to any system increases its resistance to acceleration, its inertia. Resistance to changes in motion is not stubbornness or inherent property of matter. It is space-time geometry reacting to energy content, a hotter object, a compressed spring, a charged battery. All have slightly more inertia than their cooler, relaxed, discharged counterparts because they contain more energy, which curves space-time slightly more. Once gravity is properly folded into this comprehensive picture, space-time becomes truly dynamic and responsive. It no longer sits passively in the background while matter moves through it. It responds actively. Energy and momentum and curved space-time redirects the flow of energy and momentum. This feedback loop shapes stars, galaxies, clusters, and the large-scale structure of the entire universe itself. Black holes appear naturally and inevitably in this framework. They are not exotic monsters added by wild imagination or science fiction. They form as natural consequences when space-time curvature becomes so extreme that all possible geodesic paths tilt inward. Not even light, which moves at the maximum possible speed along the boundary of causality, can find any geometric route pointing outward. Time itself points inexorably toward the center. Near such regions of extreme curvature, time slows dramatically relative to distant observers in weaker gravitational fields. This is not illusion, approximation, or observational artifact. Different paths through curved space-time accumulate genuinely different amounts of proper time. Clocks tell absolute truth about their own local experience. even when they disagree dramatically with other clocks experiencing different geometry. An observer falling into a black hole experiences time normally from their own perspective, while distant observers see that same fall becoming infinitely slow, asymptotically approaching but never quite reaching the event horizon. Both observations are completely true from their respective geometric positions. At the largest cosmic scales, space-time stretches and expands. The expansion of the universe is fundamentally not matter, racing outward from some central explosion point. It is geometry itself, evolving over time. Distances between galaxy clusters grow because the metric, the mathematical object describing space-time geometry, itself changes throughout cosmic history. This allows distant galaxies to separate faster than the speed of light without violating any physical laws, because no object actually outruns light locally through space-time. The space between them grows, while they remain relatively stationary within their local space-time patches. This distinction matters profoundly. It prevents conceptual confusion, motion through space-time, and change of space-time geometry are genuinely different processes. Both are physically allowed. Both can be measured. Both contribute to observations of cosmic expansion. Separating them clearly in thought leads to clear understanding. Spacetime also stores memory of violent events. Gravitational waves carry detailed information about catastrophic cosmic events long after they occur. When two massive objects like neutron stars or black holes merge, space-time rings like an enormous struck bell, sending ripples spreading outward through the universe at light speed. Sensitive detectors on Earth sense these vibrations as tiny, periodic shifts in distance between suspended mirrors. Geometry itself becomes directly observable through these measurements. At this stage of understanding, space-time stops being abstract theoretical construction and acquires tangible physical consequences that can be touched, measured, engineered around, and exploited technologically. GPS satellites, gravitational wave detectors, particle accelerators, cosmic ray observations, all depend critically on accurate space-time description. And yet space-time remains beautifully subtle in its influence. It does not command objects where to go by force. It defines what paths remain available. Objects follow those geodesic paths not by conscious choice or guided by external forces, but simply because no geometric alternatives exist locally. This perspective clarifies deeply why space-time feels smooth and continuous at large. Everyday scales but becomes uncertain and possibly discrete at extremely small scales. On scales much larger than quantum effects, geometry averages out into smooth curves. On extreme scales approaching the Planck length, quantum effects become dominant and the smooth geometric picture may break down entirely. How space-time behaves when those quantum effects dominate and completely remains one of the deepest open questions in fundamental physics. Still, even without that final answer about quantum gravity, space-time already provides an extraordinarily powerful and unifying there. Language, it ties together motion, gravity, light, causality, and time into one internally coherent geometric structure. It replaces many separate, disconnected rules with a single, elegant geometric idea. Learning space-time well enough to teach it to others and use it practically is not about visualizing 4 dimensions perfectly in your mind. It is about recognizing and internalizing that space and time are complementary aspects of one unified system that cannot be meaningfully pulled apart without breaking consistency. Once that fundamental recognition settles deeply into understanding, Explanations become dramatically easier and more natural. Strange relativistic effects stop piling up as disconnected surprises that must be memorized separately. They line up naturally as logical consequences of unified geometric structure. Space-time does not explain why the universe exists, why physical laws take the particular mathematical forms they do, or why anything exists rather than nothing, but it explains remarkably well how those laws fit together once they exist. And that proves entirely sufficient for speaking about physical reality clearly, teaching it honestly and accurately, and carrying the fundamental idea forward without unnecessary mystery or exaggeration. Space-time becomes a practical way to describe reality that is simultaneously restrained, precise, and surprisingly intuitive once the initial conceptual leap is made, once the old artificial separations are allowed to fade away. Space-time can be treated as a working framework rather than a perpetually surprising idea. It becomes a practical tool for organizing physical laws across all scales. Instead of memorizing separate, disconnected rules for motion, gravity, light propagation, and causal structure, everything fits elegantly into a single, unified structure governed by geometry. The key principle to hold firmly is this: space-time provides the fundamental measuring system for all physical processes. Distances, durations, speeds, energies, momenta, and causal relationships are all defined within its structure. When physics predicts something correctly, it succeeds because the space-time description remains consistent across all situations and reference frames. This consistency shows up in mathematical equations, but it also shows up reliably in experimental measurements. Atomic clocks flown on airplanes return with measurable time differences matching predictions. Signals from distant spacecraft arrive precisely when space-time geometry predicts they should. Light bends around massive objects by amounts matching curvature calculations with extraordinary precision. None of these effects rely on interpretation, philosophy, or theoretical preference. They are direct measurements checked repeatedly with increasing accuracy. Understanding space-time well enough to explain it clearly to others means being able to describe confidently what stays invariant when perspectives change, measured distances and measured durations vary between observers. Space-time geometric relationships do not. Apparent forces can be reinterpreted. Underlying geometry remains, coordinate labels differ, physical structure persists. That bedrock reliability is precisely what makes space-time useful for prediction and engineering. It allows accurate prediction without appeal to hidden mechanisms or unmeasured quantities. It replaces dozens of separate explanations with one beautifully consistent framework. Once that framework becomes clear and internalized,